Okay, today we'll talk about data transformations. But before we go into today's lecture, we'll do a quick recap of what we learned last week. Okay, the model diagnostics. That's what we talked about last week, right? We'll check the if our model is valid or not by plot the standardized residuals and looking for if there are any patterns among the residuals, if there is any trend, and also we check the normality of the error by plotting a QQ plot and check if it aligns a straight line, then the error is following normal distribution. And also we check for leverage point, and what is defined as a leverage point is by looking at if this leverage is greater than 4/n, where n is the sample size. And once we find the leverage point, we would decide if it's a good leverage point or not, or it's a bad one by deciding if it's an outlier by looking at the standard residuals. Like if the standard residuals is beyond 2 or beyond 4, I mean, this absolute value of the standard residuals, well, either is 2 or 4 would depending on your sample size. So if a leverage point is an outlier, then it's a bad leverage point. We'll take some action for it. And also we are looking for influential observations by looking at its Cook's distance. And it's an influential observation if it's over 4/n-2. And also we check for the constant variance of the error. It's also called this, it's quite a long word. And we look at the scale location plot or squared standard deviation, and we plot it versus the x, which is our predictor. And most of this will be generated. Most of this plot will be generated from R command, plot of your linear regression model, linear model object. And our homework 3 will have questions asking you to do this diagnostics for your model. So that's what we learned from last week. Well, this week we talked about data transformations. So why we would need the transformations for our data? So that's when we notice there is some problem with the fitted model. We either notice, okay, the variance of the error is not constant, or the data, when you plot the data, you find, okay, it's not a really linear relationship, or there is some pattern over your residuals. Anyway, you find something with your model, then we're going to do something for it to make the model look right. So the data transformations can be used to address problems like non-constant variance of errors or for non-linearity. So by doing these transformations, it will make your model prediction more accurate, because the model is assuming that data have constant variance for the errors. And also when you fit the model, you are assuming that the relationship is linear. So now by doing the transformation, you make the data relationship being actually linear, so that help you to get more accurate predictions and models. So it will help the model to improve by doing the transformations. Okay, so let's take the example that we talked about from last week. where our response is the number of rooms cleaned, and the predictor, the explanatory variable, is number of crews. So this is what we originally had from last week, and we noticed it is a linear relationship, but when we look at the standardized residuals, there is a funnel-shaped pattern among the residuals. So that means it's a non-constant variance for the error. So, well, a common way to transform the data where you find it's a funnel-shaped residuals is to take the square root. So taking the square root, it will squash the large numbers more than the smaller numbers. Or you will see this when we really make the plot after taking the square root. And when your data are measured in the same unit, you should do the same transformation for both X and Y. So it's just the natural thing, and we're trying to keep the X and Y on the same page, on the same unit. Yeah, so we do the regression again, but now taking the square root of the original Y, which is the number of room cleaned, and taking the square root of the X, which is the number of cleaning crews. Okay, now it's the new regression, what the new regression looks like comparing to the original one. I plotted the data, the regression line, which is the solid black line, and the 95% prediction interval with this red dashed line. So comparing these two plots, original and transformed. So first of all, as the scale for both X and Y would be different because we have already taken the square root of both X and Y. And also, actually, just by looking at the prediction interval, you might notice that the interval are closer to our data when you compare it to this two. So this one is a bit further comparing to this two. I mean, relatively, it gives you this this feeling. It narrows your prediction interval, which is a good thing. So well, we have. So again, this is the same plot as before, but this one transformed back. This is, if you look at the y-axis and x-axis, it's already back into the original x and y, right? So I just transformed the prediction interval and the regression line back to its original unit. So this is what they look like after we transform back to the original unit. It's even more clear in this way. Well, the prediction interval is closer to your data. So that means your prediction is of less uncertainty, and it covers your data pretty well comparing to the original prediction interval. So this is a demonstration that by doing this transformation, you are improving your data and you're improving your model and the prediction. Yeah, so this is just kind of reiterate. We transform the data to account for non-constant variance, and our prediction interval looks better by like gauge the distance from the interval from your data, actual data. So this looks nicer before we transform back, or by looking before we really check the standard residuals, and we're capturing the shape of the data. Well, now we look at the standard residuals. For the original and the transformed data, so this one has lost their funnel shape, like this one is having the funnel shape. This one looks more, they are more random, not really have some specific pattern. So now they are more or less constant. I mean, the residuals, the standardized residuals, after we do the transform. And also, if we look at the scale location plot, which is generated by R automatically when you run the plot of your LM object, we can see that the positive trend is more or less it's gone. Well, it's not so obvious here, but if you look at the detail of the data, it's the variability of the error is getting more constant, right? The positive trend part is not that easy to tell from this plot, but the constant error definitely got improved. And when we transform it back, the improvement, we can see very clear that I mentioned here the prediction for 4 crews and for 16 crews are getting more accurate because this one fall into the prediction interval, the data is within our prediction interval, and this one is getting closer. And of course, also this one. So if we really ignore the data, ignore this non-constant variance, or do the regression model like this and get your prediction interval, it's not really accurate, right? And your data, so when the non-constant variance is getting really severe, then the prediction is really invalid, and like the prediction interval will be narrower comparing to your real data. So by doing this transformation, it helps a lot. It get you back to the right model. Well, we can also do log transforms as a different transformation for our data. Especially it also helps for non-constant variance. And I put the transform, just the transformed model here. So both y and x, you take the log transform. The model looks like this. And so when you transform your data, you get some added benefits. Like this new beta 1 is actually the ratio of the percent changes in y and x. So an interpretation would be for every 1% increase in x, the model predicts a beta 1% increase in y. So so put in math, it's just the percentage change in y equals to the beta 1 times the percentage change in x. Well, this log transform is common when we're studying the relationship between price and quantity sold. As a percent changes in sales because of a 1% change in price is quantity known as price elasticity. Well, this term is not that important, but this is just a common case where we use this interpretation for the model. And this value, this price elasticity is almost always negative because the relationship between price and demand is a negative relationship. So when you increase the price, normally the demand will drop, and vice versa. So knowing this value give you idea of how revenue will change as you change the price of the goods. So if this beta 1 has, you estimated to be -5. So we know that for every 1% change in price, there will be a 5% decrease in demand because you have a negative sign here. So increasing the price of the product will result in a revenue decrease as there is a large decrease in quantity sold, this 5%, comparing to the increase from the price change. The increase of 1% for the price. Well, when you multiply this to price times quantity would be your revenue. So increasing less price but decrease loss of your sale, then the revenue would definitely be a loss.